Okay, here we go. Lights, camera, action. We are another exciting episode of AP Chemistry here at Spain Park. Today is Friday, September the 12th, okay, 2025. So today we need to finish talking about the packet dealing with attractive forces. We're going to go through and we're going to talk about several things that are in the notes. I'm going to kind of teach as we go over the questions. Yesterday at the very end of class, we kind of racing through trying to get done with some of these other questions, and I need to spend a little bit more time on those as we go through. So let's get that packet out. Let's start looking at we were working on question number 8, okay? And I want to kind of continue on that question. Question number 8. All right, so again, I want to clarify. First off, what is a vapor?
Someone who vapes.
Well, there's a reason why they call it vaping. Okay, not just a liquid or a solid, a substance that's a liquid or a solid at room temperature, but now it's in the gaseous phase, we're going to call it a vapor. So water is normally a liquid. When it's in the gaseous phase, we call it water vapor. Alcohol would be alcohol vapor. Gasoline, it says, caution, vapors are harmful to your health on the gas pump. Because gasoline is a liquid at room temperature, but it does quickly vaporize. Okay? They call it vaping because you put it into the vape as a liquid, but then when you inhale it, you're inhaling it as a vapor. You're vaping, you're changing, well, not you, but hopefully whoever does the vaping, okay? Y'all, I'm telling you, there's a lot of research coming out saying that the vaping is just as bad or worse than smoking a cigarette. Both of them are bad. Y'all get a different vice. Bite your fingernails, okay? Drink too much Diet Mountain Dew. Find a less hazardous vice if you have to have a vice. Okay? Now, when I'm looking at this is important, y'all. When I'm looking at this, okay, I have the lid on here. Right now, this is vaporizing. Now, again, the difference between vaporizing and evaporate. Evaporate simply means from an open container. Vaporizing is from a closed container. Okay, so a puddle evaporates, but we have vaporization going on inside of here. So water is evaporating, but why does the water not evaporate completely? Not enough space, so what starts happening? It starts condensing, and we reach equilibrium. The definition of equilibrium is the forward rate equals the reverse rate. The amounts don't necessarily equal one another because you have a whole lot more water molecules here than you do vapor molecules. Because vapor occupies much greater space, and you don't have as much space. So you got a bazillion more water molecules, but at some point this gets concentrated enough to where the water molecules start condensing back down into here. So the rate of evaporation now is equaling the rate of condensation, which means that we have we're going to get a constant concentration of vapor molecules above the liquid. We have an equilibrium. Now, what causes pressure? What causes pressure?
Air.
No, not necessarily, not in here. What is the definition of pressure? What causes pressure inside a balloon, inside anything? Okay, you guys, come on. This is good. This is super important stuff. I need 100% focus. Okay? What causes pressure?
Force of air.
Yes, that's the definition of it, but in here,
Limited amount of space and molecules.
doing what?
Pushing gravity.
Say that?
You can push it against the molecule.
Well, they don't really can't like push, but what they do is they collide. Okay, pressure, and you need to write this definition down. Pressure is caused by collisions of gas molecules with the container wall. Pressure is caused by collisions of gas molecules with the container wall. Caused by collisions of gas molecules with the container wall. So, if the more molecules there are up here, the more collisions with the container wall there's going to be, and thus the higher the pressure is going to be. So we have what's called the equilibrium vapor pressure. Once it reaches equilibrium, once the forward rate and the reverse rate, which happens relatively quickly in a closed container, once this gets concentrated up here, then you have the equilibrium, the forward rate and the reverse rate. So the number of water molecules, vapor molecules now is constant. Not necessarily the exact same molecules, because some are constantly evaporating, some are constantly condensing, but the number of molecules above the liquid is going to be the same. It's kind of like going to Walmart. You got people constantly going in, people constantly coming out, but you always have about the same number of people inside Walmart, no matter when you go. It's always crowded. Okay? People going in, people coming out. Water evaporating, water condensing. Okay, different molecules up here, but always pretty much the same number of molecules. Equilibrium vapor pressure. Now, if I heat this up, what's that going to do to my rate of evaporation? It's going to increase it, right? So the molecules are going to be moving faster. So the molecules can move faster, and more of them can be up here, and they're going to hit the container walls more. So we're going to end up increasing the vapor pressure. So generally speaking, if I look at vapor pressure, I look at temperature versus vapor pressure. If I increase the temperature, I'm going to increase the vapor pressure. Molecules are going to move faster, they're going to evaporate more quickly, you're going to have more vapor, and it just makes sense, you're going to have more vapor above the liquid. Okay, so if I begin to heat this up, the pressure inside is going to build up. Things are going to evaporate more quickly. Okay, so that's the first thing. We need to understand what we're talking about with vapor pressure. We can even have vapor pressure on an open container, and you can really think about the vapor pressure as the rate of evaporation. If things are evaporating quickly, you're going to have a lot of vapor, which means you're going to have a high vapor pressure. If things are evaporating slowly, you only have a little bit of vapor, you have a low vapor pressure. So now how would that relate to intermolecular forces? Hey, just hold on to it, you can throw it away later. Just put it on the table and throw it away later. Okay? So how does that relate to attractive forces? If something has weak attractive forces, if a liquid has weak attractive forces, it's going to evaporate quickly or slowly?
Quickly.
So what does that mean about the number of vapor molecules? High. So what does that mean about the vapor pressure? It's going to be high. So we can relate the vapor pressure to the strength of attractive forces, in that the weaker the attractive force, the faster, the more readily something's going to evaporate, the higher the vapor pressure. Okay? Now, we have to now relate that to boiling. So right now, evaporation, if I look at just a beaker of water, okay? I have water molecules all down in here, okay? But then I have some just kind of floating around the surface, catching rays. These are bumping into one another, average kinetic energy. This one hits this one slows down, this one speeds up, but then before this one can escape, it hits this one, and then this one slows down, this one speeds up. So they can't really escape or get away from one another because they're constantly colliding. And so as soon as one gets enough energy to break away, it hits something else, And so, but what about if a fast one hits one on the surface? Now all of a sudden, bam, it can come flying off. Evaporation, the escape of high-speed molecules from the surface of a liquid. Evaporation is only going to happen on the surface. Because anywhere down here, before they can escape and break apart from one another, they hit something else and then transfer the energy. Okay? So evaporation only occurs on the surface. But if we continue to heat this up, eventually these molecules are moving fast enough to where then they can start pushing away from one another and trying to form that bubble. And what do we say again? What's inside the bubble when water boils? Water vapor. But if this bubble's going to form, what's going to happen to the level of my water right here? It's going to rise. Is there anything resisting that water from rising up? Pressure, what pressure? The atmospheric pressure. So the atmosphere is pushing down here, saying, no, bubble, you can't form. So as long as the atmosphere is pushing down with a greater force than the vapor pressure, the molecules are trying to push out, the bubble can't form. Now, you got more and more high-speed molecules, so a bunch of these are getting hit on the top, and so you see the steam, so the rate of evaporation is increasing, but no bubble can form. Until the vapor pressure equals the atmospheric pressure. So here's the next thing you write. Boiling occurs when the equilibrium vapor pressure equals atmospheric pressure. Boiling occurs when the equilibrium vapor pressure equals atmospheric pressure. Boiling occurs when the equilibrium vapor pressure equals atmospheric pressure. So normally, we just put the pot on the stove and we begin heating it up, and the vapor pressure of the water increases until finally the vapor pressure equals atmospheric pressure, which for water occurs at 100 degrees Celsius, and the bubbles begin to form. That's when the vapor pressure of the water equals the atmospheric pressure. But the atmospheric pressure changes every day. So today, I just checked, and it's the normal atmospheric pressure. Now, we're in America, so we do it in terms of inches of mercury. Normal at 1 atmosphere of pressure is 29.92 inches of mercury. The rest of the world uses millimeters. What would that be in millimeters? What's the standard pressure in millimeters of mercury? Okay, 760. I heard it's 60, 760. So 760 millimeters is the exact same distance as 29.92 inches. Right now, so that's normal atmospheric pressure. Okay? But pressure changes every day. We're at 30.15. So we're at a little bit of a high pressure. That's why we have good weather. High pressure is generally good weather. Low pressure is generally bad weather. Okay? So we got a little bit of a high pressure, which means the atmosphere is pushing down a little bit stronger. So what does that mean about the boiling point? It's a little bit higher than 100 degrees. Now it's like 100.1 or maybe even less difference than that. Okay? It's just a very small difference, but it's a little bit higher than 100. If a low pressure system comes through, what's going to happen? It's going to be lower. As a matter of fact, I'm just going to put fresh water in here. Just take some water, just from the tap. Stick your finger in that for me. Is that hot?
No.
Okay. Ooh. That really made a mess. I just got to make sure I get a good seal. Do you need a dry clean?
No, I'm good.
Oh, yeah. Your mom would be proud you wiped it on your shirt. Okay.
Guys, come on.
Okay, so I'm gonna put this in here and get a good seal. This is a vacuum pump. What does it do? It takes it out. This thing really sucks, okay? And so, but that's because that's what it's supposed to do. All right? So, I turn this on and I begin sucking the air out. So now, there's going to be less and less air above the liquid. And in the other class, it began boiling really quickly. There we go. Okay, now, can you see it now? I know there's a lot in there. Okay, it's boiling vigorously. Is it hot? Did I do anything to heat it up? No, so what am I doing? Okay, it makes too much noise. Okay, what we did is instead of putting the pot on the stove and increasing the vapor pressure, we decreased the atmospheric pressure to where now it's boiling at about 22 degrees Celsius, room temperature. So we can adjust the boiling point of any liquid because it's when vapor pressure equals atmospheric pressure. So if we change the atmospheric pressure, we can change the boiling point. We say the normal boiling point is when it's 1 atmosphere. Now what would happen if I did the opposite? What happens if I increase it to 1.5 atmospheres? Now I'm going to increase the boiling point. That's what a pressure cooker does. A pressure cooker, you put a lid onto it that seals it and doesn't let the steam out. So then the pressure builds up on the inside. And that's going to keep the water from boiling, so when you're cooking your spaghetti noodles or whatever you're trying to boil in the water is going to be hotter than 100 degrees. Now it can get up to 120, 140. Things have cooked faster. What about in the mountains? What do we know about the atmospheric pressure in the mountains? It's lower. So what does that mean about the boiling point? It's lower. So even though when I look at this, okay, I look at this again.
It's cold.
It's still cold. It's actually probably colder. Okay? Because boiling, the high-speed molecules are the ones that are leaving. So when you boil something, it actually cools it down because the average kinetic energy as the high-speed molecules leave, it only leaves the lower ones, and so the average kinetic energy decreases. Boiling, just like evaporation, is a cooling process. So here's the nuts and bolts of this. Here's the takeaway. We just said, if it has the weaker attractive force, what does that mean about its vapor pressure? Higher vapor pressure. So if I look at alcohol, rubbing alcohol or any alcohol, okay, C2H5OH compared to water, okay? Now, here, alcohol boils at 78.9 degrees. Okay? What does that mean about the attractive forces between the alcohol molecules? They're weaker. What does that mean then about its boiling point? It's lower. So here's the relationship that you must know. The weaker the attractive force, the higher the vapor pressure, the lower the boiling point is.
You're gonna have to restart. I forgot.
Well, hold on. Oh, I guess we are going code red. It's kind of interesting. It's kind of interesting. We're all coming up here. Just pause it.